Hi again. Last time we were able to discuss the properties of determinants. The lesson for today is about the applications of determinants. So the lesson objectives are, at the end of the lesson, you should be able to find the adjoint of a matrix and use it to find the inverse of the matrix. Also use Cramer's rule to solve a system of n linear equations in n variables, and to use determinants to find the area, volume, and equation of lines and planes. Beginning with the adjoint of a matrix. Now, what is the adjoint of a matrix? Recall that the cofactor Cij of a square matrix A is negative 1 raised to I plus j times the determinant of the matrix obtained by deleting the ith row and jth column of A. So you will end up with a matrix of cofactors of A, which has the form as below. So we can see that the entries of A are all the cofactors at any ith row and jth column. Now the transpose of this matrix is the adjoint of A and is denoted by ADJ of A. Now the adjoint of A is equivalent to a matrix whose row entries are actually the column entries in your cofactor matrix of A. We're given in example 1, a 3 by 3 matrix A, wherein we're asked to find the adjoint of A. To find the adjoint of A, recall that it is equivalent to the transpose of the cofactor matrix of A. Okay, so meaning we have to find the cofactor at each ith row and jth column. Beginning with C11, we will have the cofactor 11 equivalent to negative 1 raised to 1 plus 1. So we will have negative 1 square multiplied to the minor 11, which is the determinant of the submatrix that results when deleting the first row and first column. And the minor is equivalent to 4. So that the cofactor matrix begins with C11, which is equivalent to 4. Now, instead of using negative 1 raised to I plus j, let us just make use of the checkerboard pattern of signs. So beginning with plus, so we already have 4, which is plus, and then we will have minus, plus, and then minus, plus, minus, plus, minus, plus. So all I need to do is to find the minor. So in this case, we will have the minor of 11. Minor 11 is 4. Minor 12, so deleting first row, second column, we'll be left with a submatrix that contains entries 0, 1, 1, and negative 2. And the determinant of that submatrix, which we refer to as M12, is just equivalent to negative 1. And then the minor of the minor 13, so deleting first row, third column, will be positive 2. Okay, by the way, let us close this one. And then what will be the minor 21? So the minor of 21, so we delete the second row, first column. We will have 3 times negative 2 is negative 6. Negative 6 minus 0 is negative 6. And then the minor of the minor 22. So we eliminate second row, second column. You will have negative 1 times negative 2. That would be positive 2 minus 1 times 2 is negative 2. So we'll have 2 minus 2, that will be 0. And then the minor 23, we delete the second row, third column. We're left with the following entries, negative 1, 3, 1, and 0. So the minor of the minor 23 is negative 3. And then the minor 31 is equivalent to 7. And then the minor 32 will be -1. And the minor 33 is 2 minus 0. So that will be 2. And then this is the cofactor matrix of A. And we need to transpose this one to come up with the adjoint of A. We will have 4, 1, and 2. So you have here 4, 1, and 2. Our second row becomes the second column. So you have positive 6, 0, positive 3, 6, 0, 3. And then we'll have 7, 1, and 2. 7, 1, and 2. So this will be the adjoint of A. Now let us check our answer. So you have here 4, 6, 7. And then we will have your 1, 0, 1. And then we will have your 2, 3, 2. Now theorem 3.10 gives us the inverse of a matrix using its adjoint. So if A is an n by n invertible matrix, then the inverse of A can also be determined using the adjoint, and this is equivalent to 1 over the determinant of A multiplied by the adjoint of A. So for example, use the adjoint of A to find the inverse of A. We were done solving for the adjoint of A in the previous example. And since in order to find the inverse of A, we will have 1 over the determinant of A times the adjoint of A. Now, the determinant of this matrix is equivalent to 3, and you can check that one out using cofactor expansion method. So we will have here 1/3. And then we will have the adjoint of A, so beginning with 4, 6, 7. So we have here 4, 6, 7, 1, 0, 1, and we will have your 2, 3, 2. So the inverse of A is the matrix whose entries are the following. We will have 4/3, 6 over 3, that will be 2. And then we will have 7 over 3. And then we will have here 1/3, and then 0, and then 1/3 again. And then we will have your 2/3, 1, and 2/3. So this now is the inverse of A. So you have your 4/3, 2, 7/3, 1/3, 0, 1/3, and we will have your 2/3, 1, and 2/3. Okay, you can check whether the answer is correct by using this statement that A times the inverse of A equals I equals the inverse of A times A.